Hello, welcome back to my physics lesson channel. Good morning to all my students. Okay, today early morning we got class. That's my class. There's a Form 4, Science 2. Okay, hopefully all the student is here. Good morning. Okay, anybody respond to me? Okay, let's see the student respond here or not. We got 11 is watching. Okay, I don't know you got already wake up or not. Okay, so you give me the response. You can listen me or not. You can listen me or not? Okay, anybody just on the line, you just type in the chat room. You can listen me or not. Okay, good morning, Sarah. Okay, can. Okay, so that means I can continue my lesson. This one is a part 2 because that day we just do one of the formula. Okay, for the part 1. Now I want to continue for this part. Okay, good morning. Okay, so we continue. Okay, so we go through the next one. Okay, the next one we need to find out the relationship for our gravitational acceleration. Remember the small g. Okay, the small g before that we do by calculation for free fall, is it? That's a 9.81 for the Earth. So this one we call gravitational accelerations. Okay, on the surface of the Earth, with the universal gravitational constant. Okay, remember the capital G. Okay, before that 3.1 part 1, we learned that. I call you to press the calculator using the CONST. After that 39 is it? That one is a gravitational constant. So now we need to make relationship for these two G. Okay, the name is a difference. One is a gravitational accelerations, another one should be the gravitational constant. Value also difference. Okay, now how to make the relationship? Okay, first we go to show. Okay, the small g we call it as a Newton's second law of motion. We create the formula is a F equal mg. Okay, remember this one. Normally we just write W equal mg lah because you want to find the weight, is it? Okay, from here weight also is a force. So we just write this one equation. Okay, for the Newton universal law of gravitational force, so this one what we learned before that. Okay, force, after that we got G, constant, gravitational constant, then we got capital M and small m. So capital M normally for the mass of the object is the highest one. Okay, if Earth and Sun, so that means the M bigger one should for the Sun, then the small one for the Earth. Okay, R square means the distance between the center to center. We call R square. Okay, now we need to make a relationship for small g and capital G. Okay, so we create the equation 1 and also the equation 2. Okay, now we can break it together. When we just bring it together, we can say 1 equal to 2 lah, because both also is a gravitational force. So mg now will equal to the capital G, then capital M, small m, over R square. Okay, now finally, what is the relationship? So the m actually we can cut it. Okay, the small m means object. Okay, the small object, the mass we go to measure should be the same, then we cut it. Then the capital M sure is a mass of the Earth. Okay, so now we're talking about the Earth and also the object you go to pull. So that means the object, the mass sure is a small one. And the capital M sure is a Earth, the mass of the Earth. Maybe the situation they're using the sun, using the moon, then that means we need to put this one at. Okay, they're not constant mass, Earth mass. Maybe they're using another planet is a bigger size. So we take this one, capital M is the mass for the another planet. So from here, the equation now we can create G equal capital GM over R square. Okay, so from here, this one is a relationship for the gravitational acceleration and also the gravitational constant. Okay, now you're going to see the gravitational acceleration that will be affected by what? First one, gravitational constant already is constant value, so that's not related. Okay, you see the mass and also R square. When the mass increase, gravitational acceleration increase. Okay, so this one we're talking about the outer space. That means the whole earth outside. Okay, we never said inside. Inside gravity, they sure is a fixed one. Okay, but now it's outside, talking about the earth and the moon. Mass increasing, the gravitational acceleration sure increase. Example, earth and moon. Sure, earth is a bigger size, is it? So the gravitational acceleration sure is higher. Okay, how about the r? R square is the distance between the center of the object. So that means when you just further, you find it the gravitational acceleration become less. So G and R inversely proportional. G and M directly proportional. So this one's a relationship, okay, for the gravitational accelerations. Okay, so from here they say factor that will affect the gravitational acceleration. So we got two. First one, distance between the center of the earth and the center of the object. Okay, number two is a mass of the object. Okay, so the capital M. So these two is a factor. They will affect the gravitational accelerations. Okay, so from here the relationship, distance longer. That means the distance is further, gravitational acceleration they will drop, inversely proportional. Okay, now we're going to see the diagram, then we go to explanation. Okay, first one, gravitational acceleration G, they always toward the center of the earth. Okay, this one we learned before. The gravitational pull, they must go to center of the earth. Okay, for the value for the earth gravitational is 9.81. Okay, this one is constant value for the earth only. Okay, so the direction of the gravitational acceleration, there's a distance from the center of the earth. So where the direction of the gravitational acceleration, they go to pull, they will pull until go to center. That means the direction F, they will pull, go to the center of the earth. So now we got two of the object. One is the earth, and another one should be the moon. Okay, now the pulling force, gravitational acceleration, they will pull until the center of the earth. So this one distance, center to center, there's a distance R. We put the symbol should be the R. So remember, never count from the surface to surface. We count from the center to center. Okay, so this one is a diagram. The gravitational acceleration, they pull center of the earth. So this one should be the distance. So this one is a formula. Gravitational acceleration, they pull the object, go to center of the earth. Okay, so now this one is a new formula for today's topics. Okay, gravitational accelerations. Okay, so now we're going to see the variation of the value of the G with the R. So that means we want to test, is it the distance further, the gravitational become less. Okay, so from here, they got give you some info. Okay, mass of the earth, okay, they provided radius of the earth. Okay, radius only, there's this one reading. Okay, gravitational constant. So now you need to calculate the gravitational acceleration for the 5 distance. Complete the table below. So student, prepare your calculator. We start to do calculation already. So that means when I just ask the question, you just type in the chat room what is the answer. Okay, so we go through the question. Okay, so from here they say you need to count the gravitational acceleration for different distance from the earth, is it? So the R first one sure is a surface, exactly surface of the earth. Then 2R, 3R, that means they're just further. So from here we must copy the info first. Okay, mass of the earth. Okay, this one is the mass of the earth. Then this one's a radius of the earth. Then this one is a constant gravitational. So they want to find the G. So what's the formula we learned just now? G equal capital GM over R square. So the first round, can you give me the answer for R? Then 2R, 3R, 4R, and 5R. So you give me the first. Okay? When you know how to do number 1, that means the number 2, 3, and until 5, that means you know how to do the calculations. Okay, so the student just give you one of the question, you just write there. Okay, how to press your calculator. Important, you need to train. Okay, because the value is too large. Okay, Tiva should give me the answer 9.81. Okay, we go to chat. Okay, 9.81. Okay, actually I give you already lah. Suppose the first one is a 9.813. Okay, maybe you're using the G, the constant gravitational. You press by calculator. We straightforward using the longest one. We no need to cut. Okay, straightforward to use. So something is behind is a difference lah. Normally we want to find is a 2 decimal point. Okay, so from here we get it. The answer is a 9.81. Okay, you can see continuous. Go and see the readings. When using 2R, 3R, 4, and 5. Okay, what you can conclude from here? When they just further the distance, you see the gravitational acceleration, they will drop. Okay, they continue to drop. So that means we prove already when the R square is bigger size, that means we find it the gravitational acceleration, they will drop. So from here, G and R square inversely proportional. Okay, so this one just want to prove only when the distance keep increasing. Okay, so from here we need to answer some of the question for this one calculations. So when R increase, the G will drop. Okay, what is the value of the gravitational acceleration on the Earth's surface? On the Earth's surface. That means on the Earth's surface, understood number 1. The first one is on the Earth's surface. So that means we get the answer already. We straightforward to write. On the Earth's surface, there's a 9.819 ms -2. So this one is the first answer when they ask on the surface. Okay, plot a graph. G against the R. Okay, G against the R. So that means your graph should be dropped, is it? So the graph, the shape become like this. When starting, the straightforward go to 9.81. Then after that, the continuous to drop. So the pattern is like this. Okay, G against the R. When starting is up, because you straightforward 9.81. Okay, so this one should be the R. Okay, at the radius surface of the Earth. So the gravitational acceleration 9.81. So this point should be 9.81. Okay, when starting there's a up until 9.81. Okay, after that 9.81 they continue to drop already. Because you are more further, the gravitational acceleration they will drop. Okay, they never drop straight line. This one is called inversely proportional graph. Okay, now we go through the next part. Okay, when using the graph paper to plot it, they become like this. Okay, this one is up. Exactly, this one should be the R. Okay, R here must be 9.819. Okay, after that, you continue to plot. The point is dropping. Then you draw the curved line. Then go down. So the curved line is never touching the x-axis. They just drop, then flat. Okay, so this one we can conclude before the gravitational acceleration 9.81, they keep increasing. Okay, when they just over, that means already after the surface of the Earth, okay, they will keep dropping. Okay, gravitational acceleration, they will keep dropping. Okay, so that one just now is a relationship. When I move, when it not move lah, when the object is further from the Earth, you find the gravitational acceleration, they will dropping. Okay, now the second situation, a body is at the height from the center of the Earth. So example, satellite. Okay, the satellite is far a bit, after that the round orbit the Earth, is it? So that means now the distance. Okay, distance we cannot say exactly the radius because there was sum of the height. So we can plus. Okay, now the distance is how far? Radius plus h. Okay, h is the distance from the surface of the Earth to the satellite. So we plus together. So from here, that means we need to rechain our formula. Okay, this one formula we learned before, is it? Force equal G, capital M, small m. For this one situation, the capital M show the mass of the Earth. Then the small one sure is a satellite. Then this one R plus H, that means the total distance from the center to the satellite. Then we need to square. Okay, this one is a gravitational force we learned before. Okay, then before that, we also got learning one of the force, remember? That one is for the mass one, the weight. Okay, W equal mg. Okay, now we put F, okay, equal mg also. But this one G is what? This one is a gravitational acceleration for the satellite when they're far away. So that means the G you need to plus about the distance. Okay, distance far away. So I put one more H. Okay, gravitational when the satellite just far a bit from the Earth. Okay, so these two, the F should be the same. Now we put the equation again. Okay, two equations put together. So we find it, the GH. Okay, the GH equal capital GM, capital M, bracket R plus H square. Okay, actually we just cancel the M lah. Okay, when the M just cancel, that means you only left the GH. So GH equal, okay, all the things here, you just cancel the small m only. Okay, now we need to give about the physical quantities. What's the meaning? Okay, GH actually is an acceleration due to gravity at the height h from the Earth's surface. Okay, G, everybody know there's a gravitational constant. Capital M is a mass of the Earth. Then the small one we cancel already. Then the last one, R, is the radius of the Earth. Okay, radius of the Earth. Then the H, you know lah, the distance from the surface to the satellite. Okay, so this one is a gravitational acceleration. We also use it, but this one is for the satellite. Okay, just now that one is at the surface. Now it's at the satellite far a bit. So we need to plus H. Okay, actually the formula should be the same. Just one you don't need to using the H, another one you need to using the H. Okay, so the conclusion we can make it, the further from the Earth's surface, the smaller the gravitational accelerations. Okay, so this is a formula for the satellite, far a bit. Okay, so again, the graph. Okay, this one is a when the R is less than the radius, G is directly proportional to the R. Okay, gravitational acceleration is directly proportional to the R. Okay, until when it just over, excuse me, when it just over the R, that means already radius outside. Okay, radius outside, that means you find it the G inversely proportional to the R square. Okay, the formula got square. So that means this one is the exactly radius surface. When you just over, that means you inversely proportional. Why we say inversely proportional? Because we refer this equation. Okay, the G equal capital GM over R square. Okay, so this one is a relationship. When you want to plot the graph, remember, after the radius of the Earth, that means already is dropping. Okay, gravitational acceleration dropping. Okay, now we're going to see one of the question. Okay, what we learned before, so we now go to apply. Is it understand or not? So student, you are ready, yeah? So from here, first one, the mass of the Earth. Okay, the mass of the Earth provided. The radius of the Earth also provided. Calculate the gravitational accelerations of the surface on the surface of the Earth. So it's very clear, surface. So surface, that means only radius. So from here, we need to count is a G, small g. Okay, let's see the info. Okay, first one is Earth, the mass. Okay, mass of the Earth. Okay, number 2 is the radius of the Earth. Okay, number 3 is a gravitational constant. Okay, this one you must know because you press the calculator, then you know the equation. Okay, last one. They want to find is a G. Okay, it's a G. So what I need to show you, just formula. Okay, I just show you the formula, how to find the gravitational accelerations. So from here, the student, you need to press your calculator and give me the answer. What is the G? Okay, so this one's a number is big, quite big. So when you press, must be careful. Okay, so you can see any student can be respond for this question. Okay, what's the answer for G? Remember the gravitational constant, you just press CONST 39. That equal, that's a value already. Okay, so simple, you don't need to type so long. Okay, we get the answer from the Zhong Yanzi, 9.81344. Okay, Zhong Yanzi, you forget the unit. Unit for the gravitation acceleration, there should be ms negative 2. Okay, we go to chat. Okay, we put all the calculation is here. Okay, one more thing, the student, every time they forget, you need to square. Okay, forget to square, that means totally wrong already. Okay, so we go to check. Yeah, the answer is 9.81. Okay, remember to put the ms negative 1. Okay, so this one is a no problem. We straightforward apply the equation. Okay, but important, you need to know what's the info that the question provided. Okay, then we go to second question. Okay, second question. Rather imagine the satellite orbit around the Earth. Orbit around the Earth at the height. Satellite is at the height. So that means you need to plus the h. What is the value of gravitational acceleration at the position of the satellite? Okay, so now they want to find the G when they're at the satellite. Okay, info. First, mass. Okay, we know the mass of the Earth. Okay, radius of the Earth also provided. Okay, gravitational constant also provided. Okay, some info extra. Okay, height. Okay, the height is a 480 kilometer. So kilo you need to convert become meter lah. So the last one they want to find G, gravitational accelerations. So from here we need to show the formula first. Okay, the formula now you need to add one more. There's a H. Okay, after H in the bracket, then square. Okay, we're going to see any student can answer this question or not. Okay, we're just waiting the student to answer it. Okay, the rest, the student, you also can type it again and show here the answer. Okay, we know the student understand or not understand about this subtopic. Okay, anyone? So be careful when you press the calculator, but slowly, one by one. Okay, don't straightforward, give me the whole things. Okay, T-Vash, give me the answer 8.486. Okay, but every time no unit one. Okay, remember the unit again. MS negative 2. Okay, we go to check. Is it T-Vash answer is correct or not? Okay, so we put all the things in. This one is a G, then this one is a M, then this one is a radius, plus distance. Okay, then square. Okay, so we continue to see the answer. Okay, 8.49. Yeah, 486 is correct. Just forget to write unit only. Remember, you need to put unit. Okay, so I think you press the calculator is okay already, is it? So this all thing you must more practice. Okay, you practice how to press the calculator. So that means when you just do the question during the exam, you are more got familiar to press the answer. Okay, to press the calculator, get answer. If you never try before, that means you press, you don't know which one you want to start first. Okay, so this one's a one exercise to practice you how to use your calculator. Okay, then we continue. Okay, I need to introduce another force. This one is a centripetal force. Okay, centripetal force in the motion of the satellite and planet. So the planet and also the satellite, they will orbit, okay, surrounded the earth, is it? So they got one of the force to pull it. So different force, we call it as the centripetal force. Okay, now we go and see. Okay, for position of the satellite which orbit around the earth at the uniform speed. Okay, now the satellite, they are orbit the earth. Okay, the speed should be uniform. Okay, uniform speed surrounding the earth. Okay, now an object in the circular motion, they always experiences changes directions. Agree? Because this one is around, is it? When you just move your direction, it keep changes. Okay, of the motion, even though the speed is a fix. Okay, the speed is a fix, but when you just move the direction, it changes. So when the direction just changes, we can conclude velocity changes. Okay, speed constant, because speed is only magnitude, but the velocity we're talking about direction, is it? So from here, uniform only for speed. Velocity cannot say uniform because they still changes. Okay, the direction keep changes. Okay, then we continue for this one. A force is required to change the direction of the motion of the body. So you keep moving, you also need to change direction, is it? So when you change the direction, you need some force. Okay, the force need for the satellite go to change every direction when it just turning, is it? So this one force, okay, they can act on the body which move in the circular of the motion. So what is this force? The force called centripetal force. So this one force just apply for the object. They want to orbit, they're moving surrounded the earth. Okay, so the force got pull, then make the satellite, they always turn at the same circle. This one we call it centripetal force. Okay, this one centripetal force help the satellite to change the directions. Okay, don't out from the orbit. The every time circle is the same directions. So this is one of the force to pull the satellite to come back. Don't run away. So this one forces, we call it as a centripetal force. Okay, when I just introduce centripetal force, understood? Sure got formula. Okay, because so many formula for this topic, so student must be remember what is that. Okay, so now we're going to see one of the centripetal kick first. Okay, this one is one of the thing you can design by yourself. Okay, you can DIY. Okay, first one they're using the rubber stopper. Okay, join with the one of the string. Okay, thick string. Okay, the string then join with the plastic tube. Okay, plastic tube means the center is a hollow lah. Then the string can go through the plastic tube. Okay, the string when it just go through until the end, you hang one of the slotted weight. Okay, slotted weight, that means got some of the force to pull it. Okay, you put a crocodile clip. Okay, crocodile clip actually they want to fix the distance. Okay, when you put the clip here, that means the string cannot move already. So from here, make sure rubber stopper until the plastic tube, the radius, they put 50 cm. That means this one just like the radius of the earth lah. Okay, they put it 50 cm. Okay, now we're going to see the explanation. Circular motion of the radius, 50 cm. The total mass of the slotted weight and also the holder, 100 gram. Okay, this all thing is 100 gram. Okay, now you hold the plastic tube. Okay, you hold the plastic tube in your right hand. After that, the slotted weight you hold in left hand. Okay, now you start to rotate. Okay, rotate the rubber stopper at the constant speed. Okay, you go to turn. Okay, just right, you play the ball, you go to turn the ball. Okay, so after that, rotate the rubber stopper at the constant speed in a horizontal circle above your head. Okay, now you see how to rotate. Okay, we explain first. Make sure that the crocodile clip stay at the distance about 1 cm from lower end of the plastic tube. So this one crocodile clip you put around 1 cm lower than the plastic tube. Okay, and also the plastic tube so that the radius is fixed. So that means you want make sure 50 cm. Okay, don't let the string to move already. So this one we make sure. Now you want to rotate, make sure the radius already is a 50 cm. Okay, the situation you go to turn is like this. Okay, you hold the plastic tube. Now you go to turn the rubber stopper. Now you can see the rubber stopper, they move in circle, is it? Okay, they move in a circle, mean this one is a radius lah. The radius just now you control already, there's a 50 cm. Okay, now you can see some situations. Now release the slaughter weight and continue to rotate the rubber stopper. Okay, now you're going to try. Don't put slaughter weight. Then you go to rotate. Okay, so when you go to rotate, you find it that easy to rotate and not easy to rotate. Okay, if don't have any weight to pull it, just like don't have any force to pull. Okay, you find it that easy to run in a one same circle or not. Okay, actually this one stands for what? Centripetal force. They go to pull, is it? When they pull, that means you find it the planet, the satellite, they can move in a round circle. That's a completely. If you don't have any slaughter weight, you find it, the rubber stopper, they cannot move in the same circle. The circle, they will be run away. Okay, you can try by yourself. Okay, number 6. They call you to repeat 1 and 3 with the total mass 200 grams. Just now is 100, is it? Now you increase the weight. Okay, you compare again. The speed of the motion of the rubber stopper with the speed in the step 5. One is 200 grams. How about the speed? One is no weight. How about the speed? Okay, then the last one is repeat the step 6. Okay, when the rubber stopper is rotating, pull lower end of the string downwards. That means this one string, you pull downwards a bit. Okay, when you pull downward a bit, means what? The radius becomes smaller. Okay, the radius becomes smaller. So from here, feel how the tension of the string. Okay, radius becomes smaller, that means your circle later becomes smaller lah. So how about the tensions? So this one is what you need to think about that for these situations. Okay, so from here we can see some of the short video about this centripetal force kick. Okay, they just go to keep swinging. Okay, so the situation should be like this lah. So you can try in your house, start to do this one situation, then you feel it, some different situation, what you can get the result. Okay, so from here we go and do some explanations. Okay, so when the rubber stopper make a circular motion, the stretch string exert a force on the rubber stopper. Okay, you got some force to acting to the rubber stopper. What is the direction of the force? Okay, because you got slaughter weight, is it? Slaughter weight sure got one of the force acting. Okay, acting from the rubber stopper. After that, they can move one of the circle. So this one force, they ask you the direction of the force is go where. Okay, because this one is put, so normally the force must go to the center lah. Okay, must from the center pull the rubber stopper. So from here, the answer is in a direction toward the center of the circle. So the force is pulled from the center. Okay, so number 2 is what is the relationship? Okay, relationship between the speed of the rubber stopper and the centripetal force. How about this one speed related with the force? Where the force to come? The force is come from the slaughter weight. So means when you put 100 gram, when you put 200 gram, how about the speed and also this one slaughter weight will affect it. So from here we find it, when you put the speed is more, they will swing faster. Okay, so from here they say when the speed of the rubber stopper increases, the centripetal force is increased. So that means just now you never put the weight, another one you put the more heavier weight, then you go to rotate. Then you find it no weight one sure slower. When got weight to pull down, that means you can swing faster. And the last one is, how does the centripetal force change when the rubber stopper make a circular motion with a small radius. Just now the last one, like you to pull the crocodile clip go downward, is it? That means you make the radius become smaller. Then they ask you about how about the forces. Okay, the forces when you make it become shorter, first one, the tension sure higher. Okay, because now the string becomes smaller already. You want to pull to make the circle become smaller. So from here, the increase of the tension of the string. When you make it become smaller, the tension higher. So understood, centripetal force also increase. Okay, so this one is what one of the example activity you can try. After that, you can test. So the pulling force go downwards actually is a centripetal force. Okay, they're just like the planet that moves surrounding the earth. So that's why they find it the moving of the satellite, how they can got forces to change the directions because got the centripetal force to pull it. So that's mean when they just rotate, they will change the directions. Okay, so they never out from the circle shape. Okay, so the situation should be like this when you just swing. Okay, when you just swing, they got all the tension to acting from the center of the earth. So that means when you make it become shorter, the tension higher, the centripetal force will become stronger. So every part you can find the velocity changes because of the direction changes. Okay, now we're going to see centripetal force. What is the definitions? Okay, there's a one of the force acting on the body in the direction towards the center of the circular. Okay, center of the circular for a body in circular motion. Okay, that means one of the force to pull the body go where? Go to the center. Okay, when the object is moving in a circular motions. So this one we call centripetal force. Okay, now we're going to show the centripetal force take off formula. Okay, the centripetal force formula is related with the velocity lah. So from here, F equal mv square over the r. R is a radius from the center to the object to rotate. So this one we call R. Okay, so from here, the name F, centripetal force, mass for the object mass. Okay, linear speed. That means the object go to moving the velocity is how many? There's a V and the R should be the radius of the circle. So this one is a centripetal force formula. Okay, now you can try example 3. Okay, a figure they show about the hammer. Okay, hammer the through the athlete swinging an iron ball. Okay, in a horizontal circle before releasing. Okay, so from here, what is the centripetal force that act on the iron ball when the iron ball is moving at a constant speed is 20? So the question they want to find centripetal force. So what we can get the info, we see the diagram that got length. Okay, the length of the iron ball. After that, they got mass of the iron ball. So we show the info first. The mass of the ball, velocity of the ball swinging, 20. Then the radius, okay, radius of the circle, there's a 1.8. Okay, now they want to find centripetal force. Okay, centripetal force means something that's a rotate, they got one force to pull it, then we're using the centripetal force. So from here, the student, we just apply the formula for centripetal force formula, F V square over R. Okay, we get the answer from the student. Okay, anybody here, just press your calculator, then you show me the answer. What is a centripetal force when you're just swinging the ball like this? Okay, anyone? Okay, we just wait the student. The student going to press the calculator. After that, give me the answer for this question. Okay, how many is watching now? Only 24 students is watching only. So you can see. Okay, Chanel, give me the answers. 1,600. What's the unit, Chanel? Okay, the unit force. Remember, don't forget. Okay, so we're going to check is it answer correct or not. Huh? Okay, we just take mass 7.2 multiply with the velocity, remember, got square. Okay, JN, give me the answer is correct. 1,600 Newton, remember, got unit. Okay, then we continue to see calculations. Okay, 1,600 Newton. Okay, correct, Jaan. Okay, Caddy also correct. So from here, this one is a one simple of the question. Important, you know the informations. Okay, then we continue to the next part. Okay, now a satellite orbit the Earth. Okay, without being driven by the rocket engine. That means they no need using any engine, but they can rotate. Okay, they can rotate, orbit the Earth. So from here, you can see the first one. The object they launch from the P with linear speed v. Okay, so when starting, they start to launch lah. So from here we got two parts. We're going to explain first. Okay, object launch with low linear speed. Okay, when they start, the speed is low, so you find it, they will follow the trajectory one. Trajectory one means the first one. Okay, and also they will reach the Earth at the cube. That means you're using the speed is not enough, just low only. So after that, they will hit back to the Earth. Okay, when they just start by using the sufficient high linear speed, that means they move, okay, launch with the high linear speed, so you can find it. They will using the trajectory 2. That means trajectory 2 is what? The circulating the Earth. The object will not return to the Earth. They will continue to be swinging, okay, surrounded the Earth. So this one is a trajectory for free falling objects circulating the Earth. So this one is how they go to start to launch. Okay, although the launch is a uniform speed, but from here, when you just launch in high linear speed, that means you find it, they will no need using the rocket engine, but they can keep orbiting the Earth. Okay, so this one is from the Newton Isaac. Later, we're going to see what the concept they mentioned. Okay, so from here, if an object launch with low linear speed, it will follow the trajectory and also reach the Earth. If the object that launch with sufficient high linear speed, they will follow the trajectory circulating the Earth. So from here, you can see the orbit. Okay, from here, they want to demo to you. Okay, the first one. Okay, the first one you can see, they're using the small one. Okay, the speed is not high enough. Okay, then they're going to try using the highest of the speed. Okay, 7,200. Okay, until 8,000. Okay, they're going to jump. So you're going to find big enough the speed. Finally, they keep orbiting. They only keep orbiting and never reach to the Earth. Okay, so this one is initial speed, and also the another one, you make the speed become higher. So this one's from the Newton canon. So they go to test, is it correct or not, this one concept. Okay, so finally there's a prediction from the Isaac Newton. The prediction is the Newton is now reality with so many man-made satellites. They're orbiting around the Earth without being driven by any thrust. That means they no need using any force to move, after that go to round. Okay, they no need to provide force already, because they already got centripetal force to put it round the Earth. Okay, so they prove already, they no need using any jet engine. Okay, so from here, the satellite, they will always experience the gravitational force acting towards the center. So that means we got two force. One is a gravitational force. Okay, another one, the force is a satellite also got centripetal force. Both pull to each other. Finally, you find the satellite, they never move far away. Okay, they never pull to far away. They continuous follow the surrounded circle. Okay, so from here they say the satellite always got gravitational force acting towards to the center of the earth. So the gravitational force on the satellite act as a centripetal force. Okay, remember now you got two forces to pull to each other. Finally, the satellite still can keep rotating at the same height. Okay, so this was one of the thing predicted by the Isaac Newton. That means they no need using any thrust engine. Okay, so we go continue for formula. Again, the formula for forces. Just now is a G and G. Now we go to forces. Okay, forces mean the centripetal force lah. So from here, we're going to create centripetal force, okay, equal to MA. Before that, we learn about the force F equal MA, or you say F equal mg lah. Okay, but from here, we still calculate there's a accelerations for the accelerations. So from here, we can create the equation like this. Which one we can cut? Okay, we can cut is a M, the mass of the object. Example is a satellite. Okay, we can cut it. That means not related with the mass. Okay, they're never using any thrust, so not really related with any mass. Okay, so from here, after I cut it, so I find it, the A will equal to the V square over R. Okay, the acceleration is depends on the velocity. Okay, so that means when you just further, R is a distance from the center of the earth to the satellite. So when the R just further, so the acceleration becomes slow down lah. Okay, because you are far away from the earth already. Okay, are far away, that means your gravitational force and centripetal force will become less. Okay, so from here we create another formula for accelerations. Okay, so from here V is what? Linear speed of the satellite. R is the radius of the orbit of satellite. Okay, so from here we can try example 5. A weather satellite, they're orbiting the earth, okay, at the height h. H is how many? 480 kilometers. Okay, linear speed of the satellite is 7.62 times 10 power of 3. So this one is a V. Okay, the radius of the earth, there's a R. Okay, R is provided. Okay, what is the centripetal accelerations? Okay, just now the A, we call it as a centripetal acceleration of the satellite. Okay, we calculate the satellite because satellite is moving, not the earth is moving. Okay, so from here, they keep orbiting, okay, the earth. So from here, remember, now your height, okay, the height, you need to plus radius. Okay, so that means they give you the radius, then give you the height. So we need to apply the formula just now. Okay, this one is the info first. Okay, info the height, the velocity. Okay, after that we got R, radius. Okay, for this one situation, we never using any gravitational constant because not related with the gravitational. We just calculate about the centripetal accelerations. Okay, not related with any force. So from here, we just create the formula. A equal V square over R plus H. Okay, R is a radius plus the distance. So this one no square, only the distance they want to calculate. Okay, remember the linear speed is a V square. Okay, V square. So from here, the student press again your calculator. Give me the answer for acceleration of the centripetal. Okay, that means the centripetal force to pull the satellite. Then I want to know what is the satellite acceleration now. Okay, so again from the student, press calculator and give me the answer for this question. Okay, we're going to wait the student. Okay, we learned a lot of the formula today, so make sure you do some revision about this topic. Okay, so fast ready, 9.11. Jian and also the KD give me the answer is a difference. So we're going to check. Okay, now they want to find acceleration. Why got Newton? Okay, we're going to check the KD answer. Is it correct or not? Okay, we just apply 7.62, 10 power of 3. After that, we go to square. Okay, then the bottom one should be the 6.37 times 10 power 6. This is the radius. Plus, okay, remember, the height is a 480. Then you put 30 behind because there's a kilometer. Okay, the final answer. Oh, yeah, there's a wrong for KD. How come 9.11? Okay, the answer from the Jian, there's a correct, just the unit. Okay, Jian, help me to change the unit. Unit is a ms -2, not Newton. So the student need to change. Excuse me. There's a 8.48 times 10 power of, sorry, it's a ms -2. Okay, we don't have any power, only 8.48. Okay, how many to change the unit, not Newton? That's a acceleration unit, ms -2. Okay, so important is info. Number 2 is formula. So if not, we don't know how to apply. Okay, remember the situations. Okay, so our lesson only until this part. This is part 2. We still got part 3, because it was too long. So many formula for this topic. So from here, today task, what you need to do, yeah, correct, Jian, the answer 8.48 ms -2. Okay, so today the task is, okay, this one. I already upload in the 4 Science 2 Google Classroom. So for the other student, you want to download, it's okay. You just go to this link or you scan the barcode. That means you can get the answer, get the question. Okay, you also can go to the YouTube. They got one of the comment there. They already put the link is there. So that means you can click. After that, you can download. Okay, download the exercise and try to do for today lesson. All the formula you need to apply lah. So this all is related to 3.1 part 1 and part 2 what we learned before. Okay, so from here our lesson just until here. For the student, my class 1, you got Google Form. Google Form you need to fill in. Okay, you need to fill in. After that, they got one of the today lesson code. Okay, today lesson code. I also forgot is what. Today the lesson code should be, today is what topic? Today is universal law, is it? So today I go to check first. So the student, later I will tell you what is the code. I also forget what is that. So the student later first, you go through Google Form. Okay, later I give you the code, then you can go to answer. I forget what code I go to press already. Okay, so from here our lesson just until here. Later I share in Telegram what is the code for today. Okay, so thank you for your watching. So every student have a nice day. So you continue to the next lesson. Okay, bye. Okay, bye to all. Thank you for yours.